Hello everybody, my name is Pamtat Tasawong, and today I will be presenting our Arduino-powered robotic arm for the Introduction to Robotics course. For this project overview, we will be designing and assembling a functional robotic arm to perform precise articulated movements. We will also show our forward kinematics calculation model to prove that the physical robotics arm can move accurately into a valid position, as well as showing you the movement demonstration video. Our scope for this project will cover the 3D design and hardware structure, as well as the programming aspect used to control the servos.
So now, let's move on to the step-by-step process that we made for this project. For the first step, we were gathering all the components that we use, which including Arduino Maker, stepper, motor, and motor driver. Once we had all the components, we moved on to designing and printing the part. After printing the part, we carefully assembled the robotic arm structure. This involved fitting and screwing the part together and make sure that the joints were properly aligned.
Okay, for the next step is the wiring. So our main movement for this project is the stepper motors. We write and upload the control code using Arduino IDE. We use library like stepper or custom inverse kinematic code for maximizing the most precision. And the last step is to program our robot. We run initial motion tests, and most importantly, we adjust the home position. We tune the speed and also the acceleration. And to make everything work, we need to debug the code or also fix the hardware, whether it's about the tension or the friction. Yep, let's go to the next part.
Now let's look at how we calculate the positions of the robotics arms and effector using forward kinematics. This visual shows the coordinate frame of each joint, and this helps us understand how each rotation and translation affects the overall arm positions in 3D space. Forward kinematics is the process of finding XYZ positions of the end effector based on the joint angle of the arm. Since our robotics has 3 degrees of freedom, so we use the David-Hartenberg or the edge convention to simplify the math. This method uses a set of parameters such as theta or the joint angle, d the link offset, a the link length, and the last one is alpha or the twist angle. We apply this value into homogeneous transformation matrix, which we multiply step by step from the base to the end effector. In this example, we assign specific angle to each joint, such as 0, -30, and 90, and we calculate the final matrix. Here we have listed the edge parameter for each of the 5 joints. And once we substitute all this value into the respective matrix and multiply them together from transformation 1 through transformation 5, we get the final transformation 1 to 5. The results show that the end effector is located at the coordinate 0.1 meter in x-axis, minus 0.06 meter in y-axis, and 0.189 in z-axis, which is relative to the base frame.
Okay, next up is I'm going to talk about some of the main functions we are going to be using. So first is G28. This is for calibrating the robot and resetting it to home position. Next is G90 and G91. This is for changing between absolute coordinate mode and relative coordinate mode. After that, we can use G1 to change the position of the end effector by typing G1 and the position. For an example, like G1 x50, y 150, and z0. Then it will go to the position we desired. Next up is M3. This is for closing the gripper, and M5 is for opening the gripper. Another function we can use is M114. This is for getting the current position of the end effector. Next is the programming explained. So I'll be explaining the key features first. First is we have modular firmware architect written in Arduino C++. Second is that we support G-code execution like G0, G1, G28. Third is that we use a command queue for smooth and ordered execution. Fourth is that we have real-time update of actual arm position via interpolation. Fifth is that we can control multiple actuators, so the 3-arm stepper, rail gripper, laser, and pump.
Okay, let's get to the main functional blocks. Robot geometry handle coordinate conversion. It take X, Y, Z position and turn them into joint angle, so the robot move correctly. And interpolation smooth out the motion, making transition between point fluid instead of jerky. And command interpret decode instruction and turn them into action the robot can follow. And stop manage homing and limit detection so the robot can be on within the bound. And BYJ gripper control the gripper using step sequence and perfect for precise pick and place tasks. Locker provide a real-time feedback for debugging and system monitoring. Okay, so here's our configs and what we have to change first is that we have to select the baud rate to 115/200 first, and then after we change the baud rate on the serial monitor, we have to change at home stepper for or off home stepper. We have to change it to true after install in stop. If it's not installed yet, you have to change it to false. And for the next one is our inverse stepper, which we have to change when the robot is not moved the way you want. If it not moved the way you want, for example, X axis is moving on left side instead of right side, and is set as false, you have to change it to true.
Looking ahead, we have several key areas for future development. First, we plan to integrate additional sensors to enhance functionality and safety. Force sensors will provide grip feedback, helping to prevent damage to objects during handling. Ultrasonic or infrared sensors will assist with obstacle avoidance and spatial awareness. A camera module will enable visual tracking, object recognition, and possibly gesture control. We also aim to upgrade the gripper mechanism by moving a two-finger or suction-based design. We can achieve a better precision and control during object manipulation.
So this is the list of our members. Thank you for listening to our presentation, and next we will show you the example video for our project.